Lesson 30 is titled The Antiderivative. Just another way to think about integrals is really all this is. And Lesson 19b, that made a brief connection to this Lesson 30 here, mentioning that integrals are also known as antiderivatives, and that's a clue that they are related to derivatives also. So here in Lesson 30, our emphasis is going to be on how the derivative and the antiderivative, how those two are connected. Not so much about integrating, although we need to think about that too. And as is typical in mathematics, we start with some fundamentals and build on those. And so this idea here is going to be expanded further in Lesson 33, just a few lessons away. The big ideas in this lesson are for a function f of x, if you take the derivative f prime of x, the antiderivative of f prime of x, that equals f of x. So you take the derivative of f of x, you get f prime of x. Antiderivative of that gets you back to the original function f of x. And then also, if you take the antiderivative, which we might call capital F of x, the derivative f prime of x equals f of x. So instead of taking the derivative of f of x, you take its antiderivative, and we call that capital F of x. Take the derivative of that, that gets you back to f of x. So let's use some things you're familiar with to better understand the antiderivative, like example 20.7, a position function. Just a standard thing we do in calculus is something squared, a variable squared. So there we had x of t equals t squared. Think about that. The first derivative, x prime of t, is just 2t. Now, if x of t, if that represents a position in units of meters, t is a time in seconds, then x prime of t, that's a rate, right, of meters per second. We could graph both of those with respect to time. So we could do that here and here. So here, let's say this is time, and this is the dependent variable is x of t, the position with respect to time. The other one, we'll say this is time, and then this is x prime of t, the rate. So not worrying too much about the scale of these, we know that x of t, that equals t squared, so that's going to be a parabola, right? Just a standard parabola with a vertex at the origin, something like that. X prime of t is 2t, that's a linear equation, right? With a y-intercept of 0, so something like that. Now, let's say we wanted to know how far did the object travel between t equals 0, t equals a seconds. We have two different graphs there. There's two different ways we could find the answer. One way is to evaluate x of t at a, so we would just say x of a is equal to a squared. And so that's the distance from t equals 0 to t equals a. So think about it, like if this is a right here, on the x of t axis we'd be right there, and so that would equal, that point would be x of a is equal to a squared. Pretty straightforward, just that's how we'd find the distance there. So what's the other way to calculate that? Well, the other way is the area under the curve from t equals 0 to t equals a. So from of x prime of t versus t graph. So in other words, calculating this area in here. How can we do that? Well, this is our method from lesson 19 where we're estimating areas under a curve, right? Where we would have the squares equal to like a miles per hour height times a hours horizontal piece, and here we have meters per second for a height times the horizontal is seconds, so those cancel, that gives us meters, right? So the area is in terms of meters. For this particular function, x prime of t equals 2t, so when t equals a, x prime of a equals 2a, right? So the height is 2a, and so the area It's a triangular area, right? So that would just be the base. A minus 0 is just A, times the height, which is 2A, all over 2. So the 2's cancel. We're left with A squared. Same answer that we got over here with the position versus time. The rate versus time area under the curve is the same as the position versus time result. That connection right there is actually, whether you know it or not or believe it or not, it's very fascinating that it works that way. So one way to think about this is the antiderivative of x prime of t, which is the area under the curve. That gets us back to what x of t is. And that works if we specify an interval, which in this case that was from t equals 0 to t equals a. We have to specify an interval on that. But we don't always want to start at 0 though, right? So for this example, that gave outputs of 0 for both x of t and x prime of t. X prime of 0 is 0. X of 0 is 0. Both of those. So considering some other t squared types of examples. So what if we had an h of t is equal to t squared plus 10? Or a k of t, some other kind of function of t squared. That was maybe t squared minus 5,413, and so on and so on. Well, think about this. H prime of t, that equals 2t. K prime of t, what is that? That's also 2t. We could have an infinite number of derivatives of things like that, that all their derivatives equal 2t. So if we're trying then to take the antiderivative, we started with that and took the antiderivative to get back to the original function. There's an infinite number of choices there, right? It's like t squared plus a constant. We can go this way easy enough, finding a derivative, but that result, taking the antiderivative to get back, because 2t could be the derivative of h of t, it could be the derivative of k of t, it could be the derivative of x of t. To undo that derivative, meaning take the antiderivative, there's an infinite number of options we could go to. And that's why we say t squared plus c would be the antiderivative of 2t. Some things are just better understood if you just do them sometimes. So that idea there, just try to be coming back to that, thinking about how x of t, x prime of t, how those are related to each other. Look at example 30.1. Given f of x equals 2x, find a function f of x that is an antiderivative of f of x. So this might be something you want to write down. Think about, to do this, we want to think, what function, if I took its derivative, would get me back to f of x? What would get me back to 2x? Well, it's what we've just been doing here, but think also of the definition which states that the antiderivative of f of x is a function capital F of x plus c whose derivative equals f of x. That's what the antiderivative is. So start with an educated guess or hypothesis here. You've learned to take the derivatives of several basic forms. Assume lesson 30 problems won't deviate from the list of derivatives found in lesson 28. So an educated guess, especially based on what we've been talking about, would be capital F of x is equal to x squared plus a constant. So how do we verify if that's correct? How if we verify that hypothesis is correct? Take the derivative. That should equal f of x. What does capital F prime of x equal? Well, derivative of x squared is 2x. Derivative of a constant is 0. F prime of x equals 2x. That got us back to f of x. So that's the right choice. We made the right educated guess there. Look at example 2. Given the antiderivative, find f of x. So we're given the antiderivative here. So what are we talking about here? Well, if we're given the antiderivative, f of x is just capital F prime of x. So we have capital F of x equals natural log x plus c. Capital F prime of x, that equals 1 over x. That's f of x. That's the original function, we could say. Look at problem 3. Given the graph of x of t that's shown there, which of the following could be an antiderivative of x of t? So look at your choices here to start with. And you see capital X of t, capital X of t. What's the thing that says which of those is the antiderivative or could be an antiderivative? It says graph is not to scale, so just focus on the fact that the graph is linear. So what have we been saying? That antiderivative, if we know that, which we have 5 choices here, x prime of that, x prime of t, that equals x of t. It's linear, so it must be something t at a minimum, slope times t. So which one of those, if we took x prime of t, that would give us something t? Well, a, that would be 0. This would just be 1. T squared, c, t squared would be something t minus 4. So that might work. So let's leave that one alone. D would give us 9t squared. That's a parabola shape. And then E would give us a cosine t. So that's not a sinusoidal pattern. It must be choice C is correct. For that one, we get 2t minus 4. We get something t. We get a linear pattern. So some things we have to be familiar with here is what is the antiderivative, that antiderivative rule. If you see a capital letter like this in a problem like that, that's for you to think antiderivative. That's when we use those normally in calculus, is to describe what the antiderivative is. We take the derivative of that gets us back to the original function. And for a linear function, this area under the curve here, that is the antiderivative. Remember, antiderivative means integral also. So what's the integral of x of t? Okay, well that's all for lesson 30.